We all rely on time, don't we? I mean, think about it. Your GPS getting you somewhere,
Right.
those instant financial transactions, even keeping the lights on with stable energy grids, it's just, well, it's fundamental.
Absolutely. It underpins so much.
But do you ever stop and think about how we actually define a second? And what if I told you that definition? It might be about to change. Radically. Today, on the Deep Dive, we're really getting into a huge, coordinated global effort scientists are working right now to redefine the second. And they're using these incredible new tools, optical clocks.
That's the plan.
So our mission today is to explore this massive shift. What does it mean for how we measure time? And maybe, what could it mean for you?
Yeah, it's a fascinating development. For decades now, the standard second, the SI second, it's actually been defined by cesium microwave atomic clocks. Labs all over the world contribute.
The old guard, so to speak.
Exactly. And they've been brilliant. Really the bedrock of modern timekeeping. But science moves on. The need for even more precision keeps growing, and that's pushing things forward.
It really is compelling. I saw a quote from Helen Margolis at NPL, head of time and frequency there.
Oh, yes, Helen.
She was emphasizing just how vital these atomic clocks are already for, well, tons of everyday tech. So the big question is, if the cesium clocks are working okay, why fix what isn't broken? Why redefine something so fundamental?
The simple answer, optical clocks are just so much better. It's an incredible leap in precision we're talking about.
Okay, how do they work differently then?
Well, unlike the microwave clocks, these optical ones use lasers, really stable lasers.
Lasers, right.
And they use these lasers to gently nudge specific atoms, maybe strontium or ytterbium ions, things like that, into switching between energy levels. These switches happen at incredibly high, very, very stable frequencies, optical frequencies, hence the name. And those frequencies, those oscillations, they become the ticks of the clock. Much, much faster and steadier ticks than cesium clocks provide.
Faster ticks, steadier ticks. So what does that translate to in terms of accuracy?
Well, this is the really mind-blowing part. These optical clocks, they're testing out at about 100 times more accurate than the best current cesium clocks.
100 times?
100 times.
Yeah.
We're talking about clocks that might gain or lose maybe less than 1 second over the entire age of the universe, billions of years.
Okay, hold on. Less than a second over billions of years. That's almost impossible to picture.
It really is. And that level of performance, that's why there's such strong momentum, this global push to eventually redefine the SI second using these optical clocks.
That kind of precision, it must open us to things we couldn't even think about before, right? Beyond just better timekeeping. What kinds of new science or tech does this enable?
Oh, absolutely. Think about, say, geodesy measuring the Earth. With clocks this sensitive, you could potentially detect tiny shifts in gravitational potential. Maybe monitor magma flows under volcanoes or sea level changes with far greater resolution.
Wow. So like geological early warning.
Potentially, yes. Or in fundamental physics testing, if fundamental constants are really constant over time.
Yeah.
Or even searching for certain types of dark matter that might subtly interact with atoms.
Okay, that's huge. And it sounds like this new study we're looking at was designed to really test this potential on a global scale.
Exactly. It was described as the most extensive coordinated comparison of optical clocks to date. This wasn't just a couple of labs phoning each other up.
Right.
No, this was a huge effort. Researchers ran their clocks and the links connecting them all at the same time across 6 different countries, thousands of kilometers.
6 countries simultaneously.
Yes. The study, it was published in Optica, involved 38 distinct comparisons. They call them frequency ratios, basically checking one clock's tick rate against another's.
38 comparisons.
Using 10 different optical clocks, all running concurrently. And get this, 4 of those specific comparisons had never been done directly before, and lots of the others were measured way more accurately than in the past.
That sounds incredibly complex to manage.
It was. Marco Pizzicato from INRIM in Italy, he pointed out that these measurements give really critical information about what work is still needed before these clocks are ready for prime time, for redefining the second.
Okay, so it's a progress report as well.
Definitely. But he also stressed how this experiment created this amazing distributed lab across Europe. He said it could be used for tests of fundamental physics, like you mentioned, searching for dark matter, testing gravity, basically using the clock network as a massive sensor.
A distributed lab. That's a great way to put it. The coordination must have been immense. I think Rachel Godin from MPL coordinated the whole multi-institutional group. Imagine juggling all those teams and timings.
Yeah, the logistics alone are impressive. It was an EU-funded project, a huge collaboration.
And someone else, Thomas Lindvall from VTT Mics in Finland.
Ah, yes. Thomas.
He made a really interesting point about why doing it this way all at once was so important, didn't he?
He did. He said that comparing multiple clocks at the same time and using more than one type of link technology provides far more information than the mostly pairwise clock comparisons that have been carried out to date.
So instead of just A versus B, it's AVSB, BSC, AVSC, and maybe even comparing them using different methods simultaneously.
Exactly. It gives you a much richer, more robust data set. You can cross-check things, spot inconsistencies much more easily. It's like getting multiple perspectives on the same event.
Okay, so let's talk about those links. How on earth do you compare clocks that are potentially thousands of kilometers apart with the kind of precision we're talking about? The study used two main ways, right?
That's right. Method one was using satellite signals.
Right.
Think GPS, essentially.
Okay, like we use for navigation.
Pretty much.
Yeah.
The big advantage there is that, well, GPS signals are available everywhere, so all the clocks in the study could use this method.
But the downside?
Precision. It's good, but it's limited due to measurement uncertainties. You've got signal noise, atmospheric interference, instrument limits, stuff that adds tiny timing errors. Good, but not optical clock good.
Right, not good enough to match the clocks themselves. So method two.
Method two used dedicated optical fiber links. Customized fibers laid specifically for transmitting timing signals with incredible stability.
Ah, like super stable internet for time signals.
Kind of, yeah. And the advantage here, much, much higher precision, about 100 times greater precision than the satellite technique, according to the study.
Wow, okay, so that's where you get the really good comparison.
That's where you get the best ones. But there's the catch. These fiber links only existed between certain labs, specifically connecting clocks in France, Germany, and Italy for this big comparison.
Ah, so limited reach.
Exactly. Though for comparing clocks within the same institute, like locally in Germany or the UK, they use short fiber links, which cut down the uncertainty even more. Almost negligible errors then.
So you've got 10 ultra-precise clocks, satellite links, fiber links, managing all that simultaneously. Were there any surprises in just making it all work together? Any unexpected hiccups?
Oh, I'm sure there were plenty behind the scenes. But one interesting finding they mentioned was, Rachel Godin pointed this out again. She said, not all the results confirmed what we expected, and we observed some inconsistencies in the measurements.
Inconsistencies, like the clocks weren't agreeing when they should have.
Sort of. But the interesting part wasn't just that there were inconsistencies, but how they figured them out. She explained that because they were comparing so many clocks at once and using more than one technique for the links.
Ah, the multiple perspectives thing again?
Exactly. It actually made it easier to identify the source of the problem. If only one link method showed a discrepancy, or if only comparisons involving one specific clock seemed off, they could pinpoint the issue much faster than if they'd just done simple A to B checks.
That's fascinating. The complexity actually helped diagnose the problems. So, given all this, the incredible precision, the successful large-scale comparison, even identifying issues, where does that leave us? The big question. Are optical clocks ready? Can we redefine the second now?
Well, the short answer is not quite yet. The study was a huge step, but it also highlighted what still needs doing.
Okay, like what?
Several things. First, those measurement uncertainties, especially over the long-distance links, they need to be reduced further. Ideally, the links should be as good as the clocks themselves or close to it.
Makes sense. The connection can't be the weak link.
Right. Then they need more data, more repeated measurements over time. This builds confidence that these clocks can operate reliably, consistently, day in, day out.
Prove their long-term stability.
Exactly. And related to that, the optical clocks need to demonstrate they can contribute regularly to generating international timescales like TAI, the current International Atomic Time. They need to become routine players, not just experimental setups.
So reliability, consistency, and better link precision.
Those are key hurdles identified in this work. And there are other criteria set by the international bodies, too, that need to be met before a formal redefinition vote happens.
So it's a process. But this study feels like a really significant milestone on that road, doesn't it?
Absolutely. It's a major leap forward in demonstrating the capabilities and coordinating the operation of future global optical clock network. It's less about if it will happen now and more about nailing down the when and how.
What a journey we've taken then, from just trying to grasp the idea of clocks losing less than a second over billions of years
Mind-boggling, isn't it?
into this incredible continent-spanning experiment comparing 10 of them at once, linking them with satellites and light through fibers.
Yeah, the scale is amazing.
And even finding that the complexity, the very thing that sounds like it would cause problems, actually helped them figure things out.
It really shows the power of collaborative science, of having multiple ways to look at a problem. It highlights this constant human drive, doesn't it? To measure things more and more precisely, especially something as fundamental as time.
Right, we just keep pushing.
And that push, that quest for better clocks, it's not just about time. It forces innovation across the board in lasers, in optics, in quantum control, in data transmission. It pushes science and tech forward and often leads to unexpected discoveries or applications way beyond just keeping time.
That's a great point. It ripples outward. So maybe a final thought for you listening. As we get closer to measuring time with this almost unimaginable precision, what could that unlock? What new frontiers, maybe in science, maybe in technology, maybe even in daily life decades from now, might open up when we can dissect time with such incredible accuracy? What happens when our grasp of now becomes almost infinitely sharp? Something to ponder.